Today, we're going to perform a PSU hack, and I'm going to show you how to build a switch mode 12 volt portable desktop power supply, and I'll achieve this by spending less than $10. This is a computer ATX power supply, and in particular, it is the FSP 500-50AAGA, which is found in some Acer and Lenovo computers. It is rated at 500 watts. However, as we will discover, we won't have, nor do we need, the full power output. For this build, I've taken the unusual step of actually doing some component layout planning, and this is the schematic that I'll be using. Because this build will only use the 12 volt rail, I've decided not to overcrowd the wiring with the voltmeter. Besides the actual power supply unit, I will use some binding posts, a lead and lead holder, a mechanical power switch. The total cost of these components is just over $3. The power supply I purchased second hand for $5. You should not be paying more than $20 for these salvaged power supplies. Because this is a salvaged second hand unit, we should give it a quick once over, just to make sure that there are no obvious signs of neglect or failure. Things to look out for include crater marks and other signs of external small explosions. By testing the voltage outputs, we'll be able to determine if the unit is running to specification. We will test against the main connector. However, all connectors should be tested, as the wires feeding connectors are sourced from different parts of the main board. This power supply has a main 12-pin connector. This is different to other ATX power supplies, which usually have a 20 or 24-pin connector. Not getting a small mushroom cloud when we connect mains power is a good start. Fortunately, there is a general wire color coding standard that is used by most manufacturers, and we will take advantage of this standard when testing expected outputs. Black is almost always ground, green is usually power on. Shorting the green wire to ground should switch on the power supply. You know that it has worked when the fan starts spinning. Using a multimeter, test your wire colours against ground. Yellow will almost always be positive 12 volts. This is the one that we're most interested in, but we will still go through all the wires and note their voltages. In this unit, in addition to the positive 12 volt rails, we'll also discover a positive 5 volt rail and a negative 12 volt rail. If you have played with ATX power supplies before, you will notice that a 3 volt rail is missing. This is not a design fault with the power supply, but rather it was built to service a motherboard that had no need for 3 volts. Once we're satisfied that the unit is operational and voltages are within limits, it's time to start dismantling. 4 screws and a little bit of a struggle with the cover and the fan, and the power supply unit is open. At this time, it's probably worth noting that even though we're not mains connected, that large capacitor is currently fully charged. Shorting across the capacitor contacts, like maybe with a finger, will discharge the capacitor faster than a southern state policeman getting First Amendment fraud to compliance with a taser. If you are on the receiving end of a capacitor discharge, it'll feel just like a taser shot. My recommendation would be to avoid this experience. However, if you're hell bent on experiencing it, do it properly and try shorting the capacitor with your tongue. The fan assembly is typically the biggest dust collector on a power supply. Now that the fan is disconnected and the tether to the power supply mainboard has been removed, brush away any debris. You'll be glad you did this task now. This unit is surprisingly clean, so I'm very hopeful that this power supply has not had an abusive life. Using the dimensions on the schematic, measure and drill the holes required to accommodate the selected hardware components. The video here shows various angles of this process. The process will need to be adopted or modified for different power supplies. But things to look out for include 1. Ensure that there is sufficient space between where you intend to mount the components and any underlying components, including the input power socket. 2. There should be sufficient space here to fold up wire service lengths so that the cover can be removed in the future. 3. Any wires that need to be housed within the power supply should avoid contact with parts that might heat up. And the parts that heat up, they're the ones that, if you look at your main board, have got a heatsink connected to them. And finally, any service wires that need to be stored in the power supply case should not interfere with fan operations. If the power supply that you're using has absolutely no space to house the electrical components that you want to use, then you'll either need to abandon your selected power supply or consider using the existing cables outside of this power supply and housing the whole lot in a larger, more accommodated enclosure. Some of the newer slimline power supplies that may be found in thin client machines or server power supplies fall into this category. It might appear obvious, but supporting the thin metal power supply enclosure when adding your drill punch marks and when drilling will make hole placement and drilling significantly easier and much more accurate. Although not shown in this video, larger drill holes are better started with smaller pilot holes. And finally, make sure that any burrs are removed from the hole edges, as we don't want these burrs to compromise the wire insulation integrity and short out against the power supply case. That would be, after all, shocking. There's not a lot of narrative that I can add about fitting binding posts. This is a pretty basic operation. The only thing that I would add is that the type of connector you include at this stage is either going to be something very specific to the application that you're building the power supply for, or the connectors are going to be universal standard format, as is the case here. The binding posts seen here will accept banana plugs, horseshoe connectors, ring connectors, or strip wire directly through the needle post hole. Computer power supplies come fitted with a bucket load of different voltage rails. These are typically 12, 5 and 3 volts. The rails are terminated with motherboard plug compatible terminators. The terminators can all be removed. As already mentioned, this particular power supply, because it is very specific to an Acer or Lenovo type mainboard, does not have the 3-volt rail. Sorting these wires out now will make wire management a lot easier. Closer inspection of the power supply mainboard identifies different 12-volt connection islands. Referencing the specification panel of the power supply identifies that the plus 12V3 group is able to provide up to 18 amps of power. Now 12 times 18 will provide us with a total maximum of 216 watts worth of power. We will use this group to supply our binding posts. Having identified the wire groups that we want to use, we'll now trim and terminate these wires together. We will be bundling 3 of the 12V3 wires and 3 of the ground wires together. Combining the wires together will have the effect of allowing higher currents to safely flow through the wires as they are seen as one thicker wire rather than 3 thinner wires. Terminate and heat shrink insulate these connectors to ensure that they are all electrically isolated. And by the way, and this is a selfish plug for my merchandise, check out Ricardo's DIY t-shirt on the screen, being worn by that Adonis of a man. My R-rated merch is available from cafepress.com/Ricardo's DIY. Further information is available in the video description or in the video end screen. Observant viewers will notice that I originally laid out some bullet connectors to feed the binding posts. Now you'll see some spade connectors. In this case, I was not satisfied that the bullet connectors provided a secure, insulated enough connection. So, off camera, these were removed and better insulated spade connectors used. In this part of the video, I also opt to use quick connectors for the LED and the power switch. These were used in preference to either direct solder connections or other spade connectors, so as to facilitate quicker disconnections should my intended power supply use changes in the future and the unit needs to be opened up again, maybe many times. There will be little if any wire movement once the cover is screwed back on again, so these connectors will provide the flexibility that I need. in line with maintaining future power supply flexibility, use and modification. Rather than removing the remaining power rails and the spare ground wires, I chose to trim and insulate them and tuck them out of the way on the side of the motherboard inside the power supply case. This step is optional, and they could have been desoldered from the motherboard instead. Now that the unit is all back together, let's check the output voltages on the binding posts. 12 volts, perfect. It is also probably time to check that what we have built looks a little bit like what we designed. Fortunately, there are no surprises here, so I think that we may have nailed it. What we really need is a real-world test to confirm that this unit will perform as intended. I'll use a coil of LED strip lights rated at 12 volts and, no surprises, it lights up as expected. I know that I've not performed the load test yet. I'll add my multimeter to the posts and set it to measure amps. Then I'll add a load to the unit until it reaches its maximum amperage output. And then I'll push it just a little bit further to see what the safety tolerances might be, and if the unit's internal overcurrent protection kicks in. Overall, this build was relatively straightforward and easy to execute. The original intention was to make a 12 volt power supply that is portable and has a wide capacity to perform the work that I intended to do. Most importantly, this build costs less than $10 to complete, and I think that's a great outcome. Thanks for watching this video. Please like, share and subscribe. Comments are always welcome.